Okay, I'll go ahead and start now. Seems like a lot of people are here already. Hi, everyone. I'm Carlo Giacometti. I work for Wolfram Research, and today I will talk about audio fingerprinting. So the talk is divided in a few sections. First, I will try to explain what is audio fingerprinting, why it is interesting, what it can teach us, and how we can achieve it. And then I will present a couple of different algorithms. One quick note that I wanted to make here is both of these algorithms are somehow dated. They both come from around 2010, 2015. However, I chose to present these ones because they are very informative and interesting on how the internals of the process of fingerprinting work. So I'll just go ahead and start on what fingerprinting, audio fingerprinting is, and why it is difficult for a machine. So audio fingerprinting is the task of recognizing a recording. And this is reasonably easy for a human, right? So here I have three signals. The original one, which is a song by Sly and the Family Stone. A compressed version, that is just the original one, saved as an MP3. Sounds pretty crappy, but still very recognizable. And then a corrupted version. I took the original song, played it through my laptop speakers, and recorded it with the laptop microphone. There is a delay, it sounds really bad. Horrendous. But it is pretty evident to, I assume, all of us that these are the same song. However, if we look at it like a machine, we just look at the data underlying this, these audio objects. These are quite different. Here I'm trimming 1 second bit from the compressed version and the original version and looking at the difference between those. And we can see that this difference is definitely not zero. So how to teach a machine how to figure out that these are the same song? So we need to extract some feature that is independent or very robust, at least, to the corruption of our signal. Waveform is not great, as we've seen. Just a compression operation, you can see that the difference is definitely different than zero. So that is a no-go already. We're not even talking about corruption here. Just compressing it and saving it as MP3 destroys the waveform in a dramatic way. So a starting point would be a mixed time and frequency representation. While the absolute values of it can still be affected by compression and corruption, the shapes and the features should be relatively robust, at least from an image processing point of view. And in Wolfram Language, the computation of time frequency features is achieved by the short time Fourier transform family of functions. So these are some examples. I will show you here the spectrogram for the three signals that we listened at. And you can see, sure, they are different, but the kind of shapes that are in the various signals are kind of solid. So we will use this as our starting point. And what is the starting point? Well, it is a short time Fourier transform, which consists very simply into partitioning the waveform into blocks and applying the Fourier transform on each of them. So here we go. We have, this is one such representation. This is just a giant array, and each point at coordinate I and j will represent the energy of the signal at time I and frequency j. So we will use this as a starting point to handcraft a set of features that are robust to compression and corruption. We will then compute a set of fingerprints for each entry in a database of songs and match an unknown songs to, well, hopefully match an unknown songs to an entry in the database. So the first algorithm that I want to talk about is the Kernel Print algorithm. This is used in services and applications like Music Brains and AcoustID. for example, and this is common in many open source applications. One example that uses AcoustID and MusicBrainz is the VLC video player, which maybe some of you have used. So the algorithm itself is not overly complicated. There's a pre-processing step. The spectrogram is computed, as we've seen. And then the whole thing is centered around the computation of these chroma features. It's just a derivative of something that is derived from the spectrogram. I will go in more detail in the next few slides. And there are a couple of filtering passes over these features, a dramatic filter pass over the result, and then a compression operation that will allow us to reduce the amount of data that is produced in a very dramatic way. So let's start. What are these chroma features? Well, they are the answer to a very simple question. So you are listening to a signal, and you want to know which notes are being played at each time. So one small detail I need to clarify is when I say note, I really mean that the information about the octave in which the note is being played is being forgotten. So if I play, for example, an A in the middle of the keyboard or an A at the top of the keyboard, those will both be classified as A. So the absolute octave of the note is irrelevant for this computation. So the starting point is we need to construct a mapping between the bin index of a spectrogram to a frequency, and then the frequency is then mapped to an absolute note. And this plot here is an example of such mapping. We can see, for example, that bin number 100 will have a note that is corresponding to an index of 2. We don't care about what the note is, if it is an A or if it is a D sharp or whatever. We just want to have a set of 12 unique identifiers. And using this mapping, we can create a list of coefficients that we will then use to filter the spectrogram. And this is a plot of all of our 12 filters, and this is the plot of a single filter. You can see the energy of each bin in this interval will be ignored, and then the energy of the bins in this interval and this interval and this interval will all be summed together. So hopefully we'll get information about which notes is played at what time. So given this knowledge, we can put all of the pieces together and compute the chroma features. I am using our original audio signal, our Sly and the Family Stone song. You can see that this is a pretty minimal implementation. There is a sampling step, and then a filter bank preparation, which are the filters that we saw in the previous slide, a spectrogram computation, and then we just take the dot product between the spectrogram and the filter bank. And what we obtain is a sequence of vectors of length 12. We can visualize, you can see the x-axis is time, the y-axis is our note index. Then we can, the next step is some time axis filtering. You can see here, our signal is convolved with the simple triangular kernel. So everything is spread out along the time axis. And finally, we normalize each time slice. You can see here the areas that had lower intensity now have intensity that is comparable to all of the other times. So this is our starting point. This is our chroma features as a function of time. The next step is feature summarization and compression. First of all, the array that you just saw is partitioned into blocks of length 16. And here we go. And this is the result. You just get a sequence of arrays of 12 by 16 elements. And a collection of 16 preset filters is computed. Here the colors are black for -1, white for 1, and gray for 0. And each filter is then multiplied to each of our partitions. These are funny shapes. The shapes and parameters for the filters were optimized using a machine learning algorithm by the author of the algorithm, and they were optimized over a large data set. So each of the windows, each of the blocks is passed through all of the filters. So each multiplication produces a single number. So per each timestamp, we obtain 16 real numbers. We can visualize those again in the same way. Time axis index that this time, instead of 1 to 12, goes from 1 to 16. So we want to compress this information. So what we can do is take all of the numbers in each single vector and quantize them into 4 values and map them to gray code, which just means I take a number that is that I can represent it in just 2 bits of information. So the quantization step, the parameters for the quantization were also optimized by the author of the algorithm. And you can see that the jumps in quantization are kind of odd and definitely not at particularly round numbers or anything. As I said, these were optimized and are unique per each filter. So from a sequence of vectors of 16 real numbers, we get a sequence of vectors of 16 integers, each bound between 0 and 3. So we can compute those. So this real numbers get transformed into quantized numbers between 0 and 3. And as I said before, each of these integers can be represented by just 2 bits. So all of the 16 compressed representations can be joined together to produce a single 32-bit integer. So for example, this vector of 16 integer from 0 to 3 gets compressed in a single 32-bit unsigned integer. So in the end, we get a sequence of 32-bit integers. And this is our fingerprint, and have a nice data structure in the Wolfram language, and we can stuff it into a numeric array of type unsigned integer 32. And we can visualize it by plotting the bit representation of all the integers. Again, time axis and bit index, and each value obviously can be 0 or 1, black or white. So now we need to test this algorithm against the different signals. Here I have the original signal, our compressed signal, the corrupted signal, and a completely different signal. And I compute the chroma print of each of these signals. So a good way of comparing fingerprints is to compute the average bit error. You can see the average bit error between the original and the compressed version is very low. And we can also visualize the difference as a function of time. You can see that the difference between the original and the compressed version produces a very sparse constellation. Instead, if we look at 2 completely different signals, you can see the average bit error is much higher, and the bit-by-bit difference becomes much, much noisier. So essentially what we have obtained is a fingerprint that is extremely robust to compression and resampling. Those kind of operations have a really minimal effect on the fingerprint. However, if we compare the original signal to a corrupted version of itself, then the situation is not as rosy. We can perform this comparison by measuring the average bit error between the original signal and a time-shifted version of the corrupted signal, and we can move this time shift and see where the minimal error is to optimize the alignment. And you can see that the minimal error here is pretty large, I would say. I am not sure that we would be able to say that this is a match. This algorithm is very good for compression, but corruption kind of destroys the fingerprint in a pretty unsatisfactory way. And if you want some references, they are listed here. And by the way, the notebook and some supporting file are uploaded on the presentation page. So the next algorithm that I want to talk about is the algorithm popularized by Shazam. I am not aware of a name for this algorithm. I will call it the Constellation Method because of, and it will become clear in the next few slides why this name makes sense. This is based on the relationship between peaks found in the spectrogram. Again, the algorithm itself doesn't seem too daunting. You compute the spectrogram, you find the peaks in it, and then build these constellations, which are nothing more than groupings of peaks, and then hash the information that you gained building these constellations. So let's get into it. Again, the starting point is a spectrogram that I will visualize here as an image. And again, I am starting with the same signal that we were looking at before. The peak finding operation is a straightforward image processing operation. Is simply a dilation step followed by a subtraction between the deleted image and the original one. This leaves us with a nice map of peaks in the spectrogram. However, we want to make sure that peaks with a smaller amplitude are ignored. So then the result is filtered again by peak amplitude. And as you can see, many of the peaks disappear in this operation. So from this image, we can extract the position of each peaks. The X coordinate is the time index and the Y coordinate is the frequency index. We don't really care about an absolute value of time in seconds and an absolute value in frequency in hertz. We just care about indexing these points in a unique and repeatable way. And we can visualize all of these points on top of the original spectrogram. Obviously, there are parameters that one can tweak in the algorithm. For example, this maximum amplitude that here we are setting to this arbitrary value to have a result with more or less peaks. So if we just use the absolute position of the peaks and just identify it with their absolute time and absolute frequency, we would end up with an extremely brittle fingerprint, since any kind of corruption of compression would obliterate any number of peaks, and even a small time shift would make the absolute time indexing of the peaks absolutely useless. In addition to that, if we forget the time information and just store the frequency information, well, we are more than guaranteed that each single peak can or will appear in any number of different recordings. So the proposed solution is to group our peaks into constellations. And constellations is just a fancy way of saying just a set of more than one point. So each of these groups, each of these constellations is formed by one anchor point and a set of targets. And here, as you can see, I'm just using block map to group this in an easy way. So what information do we store per each constellation? Well, we store per each pair anchored to target, we store the absolute frequencies and the relative time difference. So we store some relative information between the peaks. We do not store any absolute time. So what we achieve with this operation is make the information that we store significantly more unique to the actual recording. Even if this specific peak happens in many recordings, the fact that this peak is followed by this other set of peaks is more and more unique to the recording that we are considering. And we can visualize the result on top of the original spectrogram. So once we have our collection of constellations, what we need to do is efficiently store them. The parameters that we have chosen mean that we have a reasonably small set of constellations. I think is like about some tens of thousands of constellations per signal on average. For sure, if you want to make the fingerprinting a bit more robust, you can, for example, decrease the amplitude threshold, or you can increase the number of targets. In this case, as you can see here, I'm just choosing constellations of five points, but you could choose to store a bigger set of targets, and this will combinatorially increase the number of constellations that are stored. So to compress this at least a little bit, or to make them unique, we hash the frequency of the anchor, the frequency of the target, and as we were saying before, the relative time difference between the anchor and the target. And as an ancillary bit of information, we also store the absolute time of the anchor. We will not use this in the matching process. The utility of this will become apparent in the next few steps. But again, the piece of information that will be used for the matching is this hash. Again, frequency, other frequency, relative time difference. And this is how one random constellation looks like. We store this in a byte array. This could be a string, whatever way your database will be the happiest with storing it. So we have a solid algorithm to compute fingerprints, so we can just apply that on a small collection of varied recordings. Here, I just selected a random subset of recordings I have on my hard drive. They vary across multiple genres. This is just a random sample of it. We map our constellation function over all of the audio signals. By the way, the code that is being used is contained in one of the files uploaded. It is not meant to be efficient. It is meant to be explanatory. So don't plan to use this for large data sets unless you're planning to give it a lot of time to compute. It can be made much, much more efficient. But that was just not the goal of this talk. Okay, so we have hashed all of our collection. And when we apply the same function to our corrupted signal, the one that sounded terrible, let's listen to it again, was recorded with the laptop microphone. There is definitely a time shift, so it is kind of problematic recording. So the simplest way to verify a match is to compute the raw number of equal hashes. And this is what this simple bit of code does. And again, here I am only considering the hashes. That absolute time information that I stored before is completely ignored. And then I am plotting the result. This is just the entry in the database and the absolute number of matches. And you can see that there is a clear winner here that is clearly above the average, which is the correct result. However, if my recording was even noisier, or if I had a significantly bigger database with things that were possibly much more similar. Interpreting the information about the raw number of matches might not be enough in all cases. So one potential solution there, one cause of that issue was if two different songs had a similar amount of matching constellations. However, these constellations would happen at very different absolute times in the song. To solve the problem, we finally can use those absolute times that we stored in our collection. So to start, we select a few candidates and we sort them by number of matches. And in this simple example, we just get the 4 candidates with the most matches. And then per each matching hash, hi, we collect the absolute timestamps, ti, both in the test and the original track. This is what this bit of code here does. And you can see per each of our values, we get these pairs, right? This is the timestamp in the original. This is the timestamp in the corrupted, in the one that we are testing, et cetera, et cetera. And the assumption that we make is that even if there is an offset, the track plays at the same speed as the original one. So all of the collected timestamps, if we plot them, timestamp in the original versus timestamp in the corrupted one, it should still form a straight line. If it's not the same recording, we should see a reasonably random distribution of points. And we can see here, this assumption is completely verified by the data that we have here. You can see all the timestamps lie on a single line. It doesn't need to, and in fact, it doesn't go through the origin because there is an offset between our corrupted, a time offset between our corrupted version and the original one. All the other ones are randomly distributed. There aren't very many, so I guess the extent to the randomness cannot be verified as much, but they definitely do not lie in a single line. So this provides us a robust algorithm that, unlike the ChromaPrint one, is very solid to heavy corruption, including time shifting. And here are some references if you want to look at details. Other possibilities that I want to just briefly mention. One paper that has been published a few years ago proposes to do a similar thing to the Shazam, the constellation algorithm, but instead of using peaks detected in the image, it proposes to use ORB descriptors from the spectrum image. And you can very easily extract those in the Wolfram language by just using the image key points with the method ORB option. The rest of the algorithm essentially is kind of similar. You produce some kind of hash starting from these points. Of course, neural networks are always a good candidate. However, they are a black box, right? If something goes wrong, you can go back and identify the exact peak that caused the corruption of the signal. So obviously, you can very easily train something to provide this kind of service. We don't have any pre-trained network that does that. However, we do have a reasonably robust feature extractor network in the net repository. And we can do a kind of a zero-order approximation of what a neural network that does this job would be. You can see we can compute some kind of fingerprint based on the data. If we search for exact matches, we obviously do not find any because this was not trained with that purpose in mind. If we do something slightly better by measuring the warping distance between the corrupted features and the original ones, we can see that the correct sample is extracted. However, this is definitely not a robust operation, mainly because this network was not trained with the goal of fingerprinting. So the results are pretty underwhelming. I could easily imagine training an autoencoder network would be pretty solid, or just fine-tuning this net model that we have in the net repository, either with an autoencoder task or with a feature, with an embedding optimization where each class is represented by the original recording and several variations of corruption of the original recording. Anyways, I think this is all I wanted to present today. I hope you enjoyed the talk. And if you have any questions, make sure to shoot them in the chat on Pathable. Yes, the Shazam algorithm, you can definitely do that. And in fact, the example that I present doesn't use the whole audio signal of the corrupted recording is just 40 seconds, but you could very easily look at portions of the test signal. I could trim this to 10 seconds, verify the number of matches. If it doesn't produce any results, record for a bit more, etc., etc. So yes, that is completely compatible with the functions that I presented here. Let me know if you have any other questions, either throw them into, well, no, yes, I think the Pathable chat is the main way to go. Yeah, again, I chose to present some dated classic algorithms, mainly because they are very instructional and it is very easy to understand what is going on step by step and how and why the algorithm works. However, compared to neural networks, there you just have a black box that does something based on the training. So hopefully this gave some insight on how the audio fingerprinting operation works and why it can work and why it might not work and why it might fail. Okay, and I guess if there are no further questions, I will stop sharing and we can close this meeting. Thank you everyone very much for attending.